Hey, good evening, AP Physics students. Mr. Curson coming at you today with a little more right-hand rule. That magnetic field interacting with charged particles today is what we're going to be taking a look at. So from chapter 20, problem 15, it looks like we have an electron in this problem, and it is moving northward, right? I always wanted to find a good coordinate system. And we're told here in this problem that the maximum force exerted on this electron when it is in a magnetic field is equal to 7.2 times 10 to the minus 13th newtons upward. So in this drawing here, we're assuming that the force is coming out of the page here. All right, so let's draw that in here. Here's my electron. It's moving north, but the force due to the magnetic field is up out of the page or coming straight at you, okay? So we're told the speed of the electron here. And of course we're told that it's an electron. So the charge must be negative 1.6 times 10 to the minus 19th coulombs, right? And what else do we know? Well, if the charge is moving straight north, and if the field is coming, or pardon me, the force due to the magnetic field is coming out of the page, then the angle between these two must be 90 degrees, all right? Or as we're going to see, the angle between the force, the direction of movement, and the magnetic field, all three of those are mutually perpendicular, okay? And then the question is, how big is the magnetic field in this region of space, and what direction does it point? Okay, so let's do the direction issue first. Okay, what is the direction of the magnetic field in this problem? Okay, so let's review our right-hand rule here. Everyone stretch here. Oh, stretch both hands a little bit. Oh, knuckles. Oh, that was oh my goodness. Okay, so now that we're stretched out, let's review the right-hand rule here. Remember, if you take your right hand, so that means if you're right-handed, make sure you put your pen down. Every once in a while I see someone writing and doing this with their left hand, means you're going to get the wrong answer. So if you're right-handed, put your pen down, and you put your hand in the direction the charge is moving. So here I see the charge is moving north, so I put my hand in that direction. Now your fingers are going to curl in the direction of the magnetic field. Now we don't know what direction that is, okay? But let's just say it was down. I would curl my hands down, and then your thumb points in the direction of the force. Well, here the force is out of the page, and here my thumb's pointing this way, so that means the magnetic field cannot point into the page. Well, what direction would it point? Well, there my thumb is pointing up out of the page, right? So therefore, the magnetic field must point this way, right? Oh, but no, that would make sense, except this is an electron, all right? There's a negative sign in there. If this was a proton and it was moving that way and the force was up out of the page, then yes, the magnetic field would have to point this way, okay? But since this is an electron, we got to throw an extra negative sign in there, right? So what we can conclude here is that the magnetic field in this region of space points east, okay? Points east. Again, let's do that one more time. Hand in the direction the charge is moving, hand curled towards the direction of the magnetic field. The force would be down into the page, but since it's an electron, I got to flip it. The opposite of down into the page is up out of the page, so indeed the direction of the magnetic field is east. Oh my gosh, that was a lot of work. Practice that right-hand rule on lots of those conceptual problems, okay? Always lots of those on the AP test. Okay, Now that we know the direction of the magnetic field, let's go ahead and figure out its magnitude. So our equation, right, is that the force due to the magnetic field is QVB sine theta, where theta is the angle between V and B here, all right? Okay, we know this direction is going to be east, so these guys are vectors, F, V, and B, although this is not a vector equation as it's written, so I'm not going to write those in there. Okay, so if we rearrange this, we would get that the magnitude of the magnetic field is equal to the force due to the magnetic field divided by the charge times the speed the charge is moving times the, sine of theta, right? A little algebra there, just moving B over here, dividing there, all right? So our magnetic field strength in Tesla would be equal to the maximum force, 7.2 times 10 to the minus 13th newtons, all right? The maximum force, by the way, occurs when theta is equal to 90 degrees, okay? So that's our force. Our charge, of course, is 1.6 times 10 to the minus 19th. Now, at this point, we're just using magnitude, so I can do plus or minus, but I know that the magnetic field's pointing east, okay? And our speed here, as we said before, was 2.9 times 10 to the 6th, and sine theta, sine 90 degrees, is 1. And if we plug all of that in, we get that our magnetic field strength is equal to 1.6 SI units, which is the Tesla, okay? And again, that was east, all right? Okay, so so there you go. The magnetic field on in this region of space points east and has a magnitude of 1.6 Tesla. That's a strong field. Maybe about the size of the magnetic field you'd get in an MRI machine or something like that. All right, nice work, physicists. Here's your joke for the day. We got a cartoon for you. Always good to have a physics cartoon. And here it goes. Why science teachers are not asked to monitor recess. Ha ha! Looks like the old physics teacher's doing a little Newton's cradle there with the kids, right? You can see the collision coming. Boop, 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 boop. Ha ha. All right, nice work, AP Physics students. Keep up the good work.